Welcome back, students. So far in this lesson, we have studied about mirrors and lenses. We've gained some knowledge about them. But then, the purpose of gaining knowledge about anything is to make use of that knowledge profitably, to our advantage. Now, we are going to use that knowledge that we have gained to understand our own lenses. What do you even mean by that? I mean our eyes. Our eyes act as lenses. The pupil acts as a lens, and then you have retina on the back of your eyes. That acts as the screen on which the image falls. When you see something, the light from that object reaches your eyes, and then the light gets refracted and forms an image on the retina. And the cells in the retina send electric signals to the brain, which the brain interprets as the image. So this is how we see things. So all these things must work together. Your eyes must be proper, your retina must also function, and the nerve signals must reach the brain for the brain to perceive stuff. If there is a problem in any of these legs, if there is a problem with the retina, if the problem with the eye, the pupil, then you can't see stuff, and that is the reason why we wear spectacles. If there is a problem with your eye. Suppose if there is no problem here, or even if the problem is corrected with the help of the spectacles, then your retina must be okay. If there is a problem with that, if it has come forward or backward, so something has happened to the retina, the retinal detachment also takes place in some rare cases. So people cannot see stuff even though they have perfect eyes. They still cannot see things because the retina is not okay there in them. And even if the retina is fine, the nerve fibers must function properly. If there is a damage to the nerve fibers, then also you can't see stuff. So for you to see anything, then all these things will have to work properly. If there is a problem with any one of them, then we can't see things clearly. Okay. But then the difference between the lens in the eye and then a lens like this, I have a biconvex lens here, a double convex lens. The difference between the lens in the eye and a lens like this is that the focal length of this lens is fixed. But the focal length of the eye is not fixed. I can say this, the focal length is 10 centimeters plus 10 centimeters by convex lens. It's plus 10 centimeters. But I cannot assign one particular number to the focal length for the eye. Why? Because the focal length of the eye is not constant. Then what is constant? What is constant is the image distance V. You cannot change the distance between the pupil and then the retina. The retina is in one place and the pupil is in the other place. So that distance cannot be changed. For example, if we take this lens and if we keep an object here, it will form an image on this side. And if we bring the object closer, then the image will move away from the lens. So the distance between the lens and then the image will increase. So V will change. If U changes, V will change so that your F remains the same. If we take the object and move it away from the lens, then this image will come closer to the lens. Again, if U changes, V changes, and F remains constant in this. But in the case of the eye, F doesn't remain constant. Only V remains constant. The distance between the lens, the eye lens, and the retina, that remains constant. But I can move things. The object can be brought closer, taken away from me. So the object, the U can change, but V cannot change. If U changes and V doesn't change, then what should change? Your F should change. So there is a range over which the focal length of the eye lens changes. Okay. So we are going to talk about that now. And once we talk about the eye lens, how the eye works, then we will use this knowledge to devise instruments that will help us see better than we normally see. So let me draw a rough picture of the eye. I have the lens here. This is eye lens, and then it's going to make a ball kind of structure. So this is the pupil, okay. And this is the retina. It is where I have the retina. Okay. So whatever object I see using this eye, then the image is formed on the retina, which the nerves, fibers, okay, they take the whole thing to the brain, and my brain interprets that interprets the image as it interprets, as we see now. Okay, so that this is how. So without the brain, you can't see it. Anyway, so this is a lens, and this is how it is. Let's say that we take an object here. Let me take an object on one side of the axis. Obviously, it can be anywhere. It can be either up or down, or it can go across this axis. Doesn't matter. Okay? But for simplicity's sake, and let me say take an object like this. Okay? So a linear object which has an infinite number of points, and each point will send out rays in all different directions, and some of them will reach the eye, and they should form the image. Okay, anyway. So let me take this example. Okay. So what do we know? We know, I can, from this point, there are many rays that reach here, right? Okay, it's here. Let me just take one ray, for example. Let me take the ray that goes through the optical center of this lens. You take that ray, it will go undeflected. We know that. The ray that goes to the optical center will go undeflected. And you see that it's here. Okay? If your eye is normal, if it has normal vision, then the image has to be formed on the retina. And this line hits the retina there. So the image should be formed there. All the other lines must also converge here. You see, that's the difference. Okay? Like with one line, now you can find where the image is going to be formed. And all the other lines should form there. Right? Because you know that the image is going to be formed on the retina. And all the lines that fall on this lens must converge there. Else this image cannot be formed. So if this image is to be formed on the retina, then all the lines which come from this must converge on the retina. And they must converge at this point, right? Because this, if you take this line that goes undeflected, it goes and hits the retina here. Which means, then this is where the image is formed. All the other lines must also be hitting here. Okay, so after refraction, they should go there. So with just one line, I can find where the image is going to be formed in the case of the eye lens. Why? Because I know my V is fixed. V cannot change. The image has to be formed here. So using that knowledge, I don't even now need a secondary. Well, even if we take a secondary, then that ray should come here. A third ray, that should form here. Then that should come and converge here. Because the image is formed there, we know it. So the only difference is that with just one ray now, I can find where all the other rays from this particular point which fall on the lens will converge on the other side. Okay? So one ray is fine. Okay? So that is the top. Then all, if we take this, for example, if we take this point, again it will go here. But it's formed here. So this point will form an image here. Again, all the rays from that point will hit this lens and get converged. Because you have to make an image on the retina. So likewise, if you take this one, bottom point, that should go through the axis, go to the optical center, and it starts fading. So notice here, this image is going to be inverted like this. Kind of curved, but it's okay. In your eye, on the retina, this is how the image is formed, upside down. Okay. So this is how you see it. If you notice here, this angle, call this as theta, is the same as this angle theta. Okay. So this angle will be the same as the angle theta. Okay. Let me take another case. So this has formed an image. Let us suppose I bring this object closer to the eye. Let's see what's going to happen. Same, okay? same object, same height. Height doesn't change, right? So this is the height. Okay? The height doesn't change. But what I've done now is that I'm bringing, use another. I'm bringing the object, the same object here. I move there. Okay. Now you see the angle changes. You see? And this will go like this. There's no doubt. That. Now you see. Now the angle has changed. Which means that I'm going to see a bigger image. Right? So if this is at some distance, this makes the outside angle is equal to the inside angle, and I'll have a certain size of the image on the retina. But if you bring the object closer, then this becomes bigger. You can even test it. Okay. You see, I hope you are able to see this pen. Okay. Now if you bring it closer to you, you see you are seeing it as a bigger pen. The size of the pen has not changed, but I keep it, I bring it closer and closer to you. Now you are seeing it as a bigger and bigger and bigger and bigger image. And that is because the angle, notice, that angle is becoming bigger. So now this is theta, I'll call this as theta r. Red. Okay? There is theta black and there is theta r. So theta r is greater than theta black. So clearly you are going to see a bigger image. So that is why when somebody shows you something when asked, somebody gives you something and so you see how good this, let's just say I got a new thing, okay, maybe a new pen or earring or something, say I got a new one, then you say, hey, give it to me. Why do you want it in your hand? So that you can look closely. Why should you look at things closely? It's because when you look at things closely, they form a bigger image on the retina. They occupy more area on the retina, so you can see more details of that. Okay. So that's the reason why you want something to be brought closer to you to look at. Okay, so I want you to understand this first. Okay. So which means that if we want to see something more clearly, then all I need to do is to bring it closer and closer and closer and closer and closer to me. Right? If it is at some distance, then bring it closer, I can see better. Closer, better. Closer, better. Closer, better. Okay? So, you see, anything could make a great angle at an appropriate distance. For example, so this is making an angle here, this theta, and now theta r is this. But now, if you bring it even closer, let's say I have brought it as close to this as possible. Okay, I kept it too close to my eye. What's going to happen? Clearly, this ray will go through this. Okay, and this again. There, notice that you would expect. See, this big image. But what's the problem with this? The problem is that when you bring things very close, then the eye lens cannot adjust its focus. The focal length doesn't change as much as to form an image on the retina. The focal length doesn't change much now, because you see, for this U to get this V, then you must have a certain focal length. Suppose I keep the object, say, 1 millimeter before me, just maybe 2-3 millimeters before me. And clearly it's going to make a big angle. You see, if you keep it closer, everything else is blocked. I can't see anything else, right? Like it's everything else, but I can't see it clearly. Even though I know that something is in front of my eye, I can't read these letters clearly. Why? If this were true, then that should be happening, right? Why is it not happening? And that is because the lens, the eye lens, now cannot adjust its focus precisely to form an image here, an exact, a perfect image here. The image is going to be formed behind this. Okay, a clear image. The rays are going to get focused and are going to get converged, maybe somewhere here. But so you wouldn't have a fine, you wouldn't have a point image here. Okay, so that is why it's blurred. You can see stuff clearly. But even if you bring it closer, you notice that you can you can have a great angle. Like now almost everything is blocked. I can also see that there is something in front of me. The pen I can see, but I can't see it clearly. Why am I not able to see clearly? It's because the image is not exactly focused on the retina. It is formed somewhere else. So at what distance? Now, before you get into there, now you can understand that the eye lens can have a constant V over some distance range, right? For example, I'll be able to see this clearly, this clearly, this clearly, this clearly, better and better, clearly. You see, and from this point forward, it is getting blurred I can't see that clearly. So there is some distance till which the focal length of the eye can adjust to form the image on the retina clearly. You can form, the f up till a particular u, the focal length f can change. It's a variable focal length, okay. The focal length can change up till a particular u. You see, u is changing, f is also changing, but v is a constant. That's what I'm saying. So you are changing u, so the eye changes its f, all the ciliary muscles, like they either make the lens bulge or thin so that it adjusts the radii of the two surfaces of the lens to produce this varying focal length. Okay? The ciliary muscles can pull the lens, push the lens, make it bulge or make it thin by pulling. So the muscles can adjust this stuff. Okay, the focal length can be adjusted by changing the radii of the eye lens. Okay. Again, everything will have to follow that formula, the lens maker's formula. Don't forget it. So anyway, but then there is some distance u, and at that distance and beyond that distance, this adjustment, the adjustment of the focal length, that is not infinite. I can't can change my focal length infinitely. I can't go from 0 to infinity in the focal length. No, I can't do that. There is a range. My focal length is not fixed, all right. But then it has a range. I can change the focal length only over that range. Beyond that, I cannot change the focal length. My focal length is going to remain the lowest, whatever I'm going to get. Okay, and beyond that, I cannot reduce it. So if I bring the object closer than a particular distance, then the image that is formed on the retina is not going to be clear, because the convergence does not take place properly on the retina. Maybe it will form, if the retina was not there, then the image will be formed somewhere down here. The image will be not here. So that is why you are not able to see this. So now I need to know the distance. So what is the distance? The distance is called as d. The u in that case is called as d. Okay? And this is approximately equal to 25 centimeters. For a normal eye, I can see things clearly up till 20 centimeters. So beyond 20 centimeters, I can see it clearly. Yeah, I can see the bus in front of me. The school name is written on the bus. I can read it. Okay, it's maybe like it's 30, 40 feet away from me. I can read it, and I can even look at the mountain over there. Okay, that also forms a clear image. It may not be detailed, but I can see things clearly. I can see the basketball court there, and then the trees here. I can see the leaves and stuff. I can see them. I can see them clearly. So at that distance, like my u can be infinity, right? Even if it is, I can even see the sun, right? I can see the moon. They're almost at infinity. And compared to these things, they're far away. The moon is 4 lakh kilometers away from me. I am able to see the moon clearly. Yeah. So I can see the stars also. They're farther away, much farther away from the sun. I can see them clearly. Right? So I can say that the upper bound for my u is infinity. Okay? So u is infinity. U max is equal to infinity. And then u minimum is what I call as d for me. And that is, as I said, is approximately equal to 25 centimeters. U minimum is D. Why do you say U minimum? Can I not bring it closer than D? Yeah, I can. But I can, if I bring it closer than D, I can see things clearly. Because my eye lens will not focus this, converge all the rays onto the retina. Convergence will take place somewhere else. Okay, beyond the retina. So I can see things clearly. So at 25 centimeters, I can see things clearly. Till 25 centimeters, I can see things clearly. But if you bring something closer than that, then I can see clearly. Even though they make a bigger angle. There is this advantage of the bigger angle, but then the disadvantage of the rays not being focused at this point, but focused somewhere else here. So I can see that clearly. So the advantage I gain in the angle is lost when I bring objects closer than 25 centimeters. So my U max is infinity, my U minimum is 25. For my eye lens to adjust its focal length in such a way that it forms the image on the retina such that V is constant. So from infinity to 25 centimeters, I will be able to see things clearly. And within this distance, if I bring things closer, then I can see more details of that image, that object. Okay? The image will give me more details of the object. And that is why, say, give it to me, let me see. Yeah, it's good. Yeah, what is it do? Yeah, I can see it. If it is farther away, I can't read what is written on the pen. But then when I bring it closer, yeah, I can read everything. Yeah, available in 4 shades, black, blue, red and green, I'm able to see. But then if I bring it closer, I can't read again. Why? Yeah, now they make a bigger angle, alright, but they don't converge on a point on the retina. I want you to understand it, and that is why I'm stressing upon it so much. Okay? So, the angular advantage I get stops at 25 centimeters. The short point of all this, the discussion that we have had so far is this. If I have an object and if I keep it at infinity, it's going to make an angle in my eye. So I'm going to call that as a visual angle. Okay? So visual angle. So visual angle is the angle the object makes inside the eye. And that will also be equal to the angle outside the eye. Okay? So if the object is at some distance, I'll have one angle, and if the object is at some other distance, I'll have a different angle. I'll have the maximum angle when the object is at 25 centimeters from my eye. If the eyes are normal, for a normal eye, that distance is 25 centimeters. And we call that as the 25 centimeters D, which is approximately equal to 25 centimeters for normal eye, is called as the least distance of distinct vision. So this is called as the least distance of distinct vision. So this is the least distance at which you can look at things distinctly. Every point is focused, so you can see things distinctly. And if you bring it any closer, you may have a bigger angle, but you can see things distinctly. So the least distance of distinct vision is D, which is 25 centimeters. And that is where the visual angle will be maximum for the eye, for the unaided eye. Without any instrument, the visual angle will be maximum when when the object is at D. So, like this. So I have the eye. Okay, so it's going to make an angle here, as we just saw. So this is the angle, and if we bring it closer and closer and closer, the angle is going to change. You can see that it's going to change like that, and if we bring it here, then the angle will change. So let us suppose this is D. Okay, so this is the maximum visual angle for the unaided eye. Okay, so the short point again is this: if I have an amoeba, which is a very, very small organism, it's a single cell organism, you know from your biology classes. We take an amoeba, and if we bring it closer and closer and closer and closer, yeah, at this distance I may not be able to see it at all because it's so small. It's a single cell organism, and maybe if I keep it here, it's very, very, very close to it. Then, and maybe let's suppose this is the size, then it can make an angle. You see, and the image. This is the size of the amoeba. And I keep it closer. You see, then the image could be bigger than the object, then I should be able to see. But the only trouble is that I can't bring it closer than this angle, this distance D. Then the focus will not take place. Even though the object is very bigger, the focus will not take place. I would hardly see anything there. Okay, so what I'm going to do now is I'm trying to increase this angle, so, the visual angle. Suppose I keep an amoeba here. Okay. Clearly, it's a very, very small thing, and it will hardly make any angle inside. It's so small that the light from the amoeba hardly makes any angle, and particularly like if it's far away from you, definitely it's not good to make the object visible to you. Okay. But what do I know? I know that an image can be made bigger than the object using a mirror or a lens. How? We've seen that. I'll do it again. Let me take a mirror. This is a mirror. Okay. So this is the F of that mirror, and this is the C of that mirror. If I keep the object between C and F, okay, between the C and F, any place between C and F, then I can express, this is the object size. So what will happen is that the image size can be made bigger than the object size. Well, if I keep the object beyond C, then the image will be smaller. But if I keep the object between F and C, you can see that the image is bigger than the object. And now, if I see this image using my eye, then I should be able to see the object clearly. Right? And this doesn't happen only for the mirror, it happens for the lens also. So if you take a biconvex lens, again, this is F, and this is C of that lens, and this is F, and this is C of that. And if we keep it here, and what happens is, this goes through F here, okay, and then this line goes through center, you see, that's where it meets. So the image becomes bigger than the object. Not only that, if I take this kind of a setup, this is F, and this is C, and let's say this is F, and this is C. If I keep the object here, between O and F, here too, the object is here, you see, even this will make like that, and you see image will be made bigger than the object. But this, here it is a real image, this is going to be a virtual image, but then there's an image which is formed. So by using a mirror or lenses, I can get an image which is bigger than the object. And if I look at that image using my eye, then clearly I can have a better visual angle. What I'm trying to say is, suppose I take this image, take this object, AB, it's of this size, right? Let's say I keep it here. So it's of this size. So this is going to make an angle here. Instead, if I take the image, and if I take that image here, and I keep the image here, at this distance, let's say it's like that. If I keep the image here, rather than the object, if you keep the image, then it's notice that that's going to make a much bigger angle. So I'll be able to see things clearly. It's going to make a bigger angle in my eye. So this is an idea about microscopes. So in the case of a microscope, okay, this is what we're actually doing. If you take a very small object and if you keep it at 25 centimeters, it still may not make the visual angle necessary for you to see it, and that is the reason why you are not able to see atoms, cells, microbes with unaided eye. You are not able to see them. But they are so small, and the light that comes out of these things make very small angles at 25 centimeters distance. So it hardly makes, it hardly excites the sensory cells on your retina, so you cannot see. But if it is bigger, if somehow can make the image bigger, and if it falls on the retina, it will make a bigger visual angle, then you will be able to see the object in this image. So this is the idea behind microscopes. So we are going to talk about what is called as a simple microscope now. A simple microscope is nothing but a convex lens. A simple microscope. The detective lens you may have seen, right? They use a handle too, then the detectives use that. That's basically a simple microscope. Okay? So, a simple microscope. Which is simply a biconvex lens. Okay. Let's see. I can demonstrate that to you. You've seen this already. Let's see. This is my finger, okay, which you can see. But now, if I keep a lens before this, you see, you will be able to see a bigger image. So this image is virtual. You are not seeing my finger, but you are seeing the image of my finger. So it's virtual and erect. You can't capture this image on a screen. So it's a virtual image, and it's an erect image. Okay, but this is actually a simple microscope. Notice that I've kept it here between the pole of the optical center of the lens and F. The focal length of this is about 10 centimeters. Now if I keep my finger here, I'm actually keeping the object between O and F. So this is the virtual image that you are seeing. The image seems to be on the same side as the object for you, as you see, and this cannot be captured on screen. Okay, so this is a simple microscope, and clearly if I move it here beyond thing, then it's a different story, right? you may probably like see it inverted or something. Okay. So, but that is different. Then you'll be able to capture that image on a screen. Anyway, so in the case of a simple microscope, I'm going to keep, so this is a lens, and I'm going to keep the object between the optical center of the lens and F. So this is where I'm going to keep the image. My U is going to be like here. If the U is here, then clearly the image will be formed on this side. And where are we going to see this image? Okay, you may have noticed. The detectors will keep the lens like that. Okay, you see, my eye is very close to the lens. So I can say that it's my pupil is almost at the optical center because it's very, very thin, lens, and my eye is nearly at the optical center. Okay, so the line that goes through this optical center, you can roughly imagine to go through my pupil too, right? It's like that. So my eye is very, very, very close to this. Okay. This is where I'm keeping. This is how I keep my eye. Okay, this is the pupil, and this is my eye. Since it's a thin lens, then I can ignore this distance, is what I'm saying. I can ignore this distance. My eye is here. Okay. So now if I keep the object here, see this distance it cannot be 25 centimeters. Why? I told you. You have to keep the object within the focal length of this lens. So it could be somewhere here. Okay, this could be somewhere here. But if it is somewhere here, then look at this. The distance between the object and myself, my eye, it is less than 25 centimeters. So I can, I can see the object clearly. But I can see the image clearly. Why? Because the image will be formed or could be formed beyond 25 centimeters. But when the image is formed beyond 25 centimeters, the image is going to look bigger, right? That's advantage here. Look at this. If it's here, then let's say I can again on this side, I'll say this is F, this C. Let's suppose this is where the image is formed. So this is where the image is formed. Okay, so this is A, B, this is my A dash, B dash, and I am going to ignore my eye now because I kept the eye here. I kept the eye very close to the lens. That's important. Okay, so I will remove this. I don't need this now. Okay. It is. I can imagine. I can take it that this is my pupil because the distance is ignored. So I can say that my pupil is almost there. It's a very thin lens, so the distance doesn't make much of a difference. So it's here because I have kept my pupil here. It is as good as keeping it here. Okay, I can ignore that small distance. So this is a very thin lens. Okay, so now this is what I got. Okay, so this is AB, this is A dash to B dash. Now, if this distance which is V, that's where the image is formed, and this will be U anyway, right? So this will be U, and this is going to be F. So U, V, F. Okay, so look at this. If this distance is more than D, 25 centimeters, D or more, then I can see the image clearly with my eye. I can see the image clearly. If the distance is less than d, if this b is less than d, I can see even the image clearly, right? Because if it's here, let's say it's formed at 15 centimeters image. I can see even that image clearly. You can experiment with it. Okay? When I keep it like this, you see I can see the object very clearly, the image very clearly, because the image is formed within 25 centimeters. But as I move it slightly away, now I am able to see it clearly, because this is not 25 centimeters. The object is not at 25 centimeters, but the image is beyond 25 centimeters. So I am able to see my finger clearly. And if I take it further and further, I will be able to see it better and better now. Okay, rather, like it's no, I can't say that actually, I'm sorry. It's a wrong statement. If I take it further, then the image is formed at a further distance. That's what I'm trying to say. Okay? So that's about it. So the image should be formed beyond 25 centimeters. Let us suppose that this is D. Okay? So this image should be formed here. If the image is formed within D, then I can't even see that image clearly. So I will adjust my U in such a way that the image formed is beyond this D, beyond this D, and it can get formed any other place. Doesn't matter at all. I will still be able to see it clearly. We know that. Okay. So with that, let's see. Let's see what's going to happen now. Okay. What is the angle this is going to make? I have this image. What's the angle it's going to make? I told you that this O, the optical center, is as good as my pupil. Okay? So I can treat this as my pupil. So notice this is the angle now this makes. Okay? This is the angle the instrument makes. The instrument makes. Okay? My eye is here, then makes. And then what is that angle? I can use tan theta thing, right? Okay. So tan theta. So tan theta I want this. This is a visual angle, right? This is a visual angle. Tan theta I is equal to A dash to B dash by V, right? A dash B dash by V. Now notice here, that's the same as this, AB by U, and it is also equal to AB by U. Okay? And if the angle is small, then tan theta I is equal to theta I. So if I want theta I, then I can say that it is either AB by U or A dash B dash by V. That's fantastic. Good. So I got the angle. Now this makes my eye. Because notice, why is it important? Let me tell you again. Why is it important? If I keep it here, I can see this clearly with my eye. But if I bring the lens here, now I am able to see the same thing clearly with my eye, because the lens forms an image which I can see. You see, this is a very good condition. Why I wasn't considering this distance before? Why did I stop with 25? It was because this wasn't focusing clearly on my retina. I have a bigger angle, which is good. But the problem is, I'm not able to see a clear picture. but I have bigger angle. But now, if I use this lens, I have a bigger angle and also the clarity of the picture. Because I am not looking at this now, but I am looking at this image which is formed at D or beyond, which I can focus on the retina, can converge on the retina. Okay, so that is the advantage. So the better the lens, for example, the better the lens, like the more powerful the lens is, then I can bring it closer and closer and closer. I can even keep it very close. But if I have a very small lens, or rather, if I have a more powerful lens that takes this and forms an image at 25 degrees, 25 centimeters or beyond, then I will be able to see this even at this distance. So now you notice I have the best of both the worlds. I have a bigger angle because I kept it here, and I have the clarity of vision because I am not looking at this now, I am looking at its image. That's exactly what's happening here. So I told you that this is 10 centimeters. So this will be less than 10 centimeters. Less than 10 centimeters, if you were to look at this object using a naked eye, I can't see it. But then, by keeping it at less than 10 centimeters, I am forming an image which is beyond 25 centimeters, D, it's right here, which I am able to see, and I get a bigger angle. So this is going to make a bigger angle now. Okay. So this angle is made bigger, and this image is clearer because it is beyond D. So I have two good things going for me. If I keep the object here, only one good thing. The angle is bigger, no focus, so no use. But if I use a lens here, then that lens takes this object, forms an image at 25 centimeters or beyond. So I have this angle and that distance. So I am able to see things clearly. I want you to understand. Okay. So it's fantastic. Now, what is the magnification you get? So magnification. Magnification is defined like this. The visual angle you get with the instrument, okay? So this is the visual angle you got with the instrument, and the maximum visual angle you get without the instrument, to the unaided eye. Okay? The visual angle with the instrument divided by the maximum visual angle without the instrument. So this angle is easy. The maximum visual angle without the instrument, the maximum visual angle you can have with an unaided eye is at distance D. If you keep the object at D, that is where you will get the maximum visual angle. And if you go take it beyond, then the angle will be smaller. But only at D, you will have the maximum visual angle. So this part is fine. Maximum visual angle without the instrument happens at D. Okay, so this is fine. And this is visual angle with the instrument. And that will vary based on where you form the image. Whether you form the image here or somewhere else. Depending on that, this angle will change. Okay? But notice that magnification is given by visual angle with the instrument divided by maximum visual angle without the instrument. Okay? Now, it's so what you get here basically. how do you get the maximum visual angle without the instrument? I told you that the maximum visual angle for this object would be here, right? If I keep it at D, the object, I'll use a different color. So if it's the same object, I'm keeping it now at D. Okay, so now this is going to make an angle. So this angle is the maximum visual angle, theta m or theta naught. It's up to you. Okay. So the ratio between theta I and theta m is a magnification, because we are getting this image first. Okay. Without the instrument, this is the image you have got so much, and now with the instrument you get this angle. So that's the magnification now on your retina. I told you that your eye is here. Okay. So this angle and this angle. So that's the magnification you get. Okay. Now, what is theta m now? The theta m or theta naught, let's use theta m, the maximum visual angle of the instrument, is what? It's going to be this height AB is divided by D. It's actually tan theta m, so that is tan theta m, and it is also equal to theta m. So the magnification m is given by visual angle with the instrument is theta I divided by theta m, and that is equal to AB by U divided by AB by D. Okay. Now we can cancel AB, and I'm going to get D by U. So the magnification is always D by U, where I kept it. So if I use this lens, okay, so D is fixed, 25 centimeters. So if I keep it here, then the magnification is 25 by this distance, maybe 8 centimeters or something. Then if I go here, then that will be again maybe 10 centimeters by or 9 centimeters by 25. So depending on where I keep this, maybe this is 5, 6. Okay. So where I keep this, I'm going to get a different magnification. Yes, I hope you understand this. M is equal to D by U. So depending on where I keep this, where my U is going to be, I'm going to get different magnification value. So which is my minimum magnification and which is my maximum magnification? So which is my minimum theta? This is fixed, can't do anything. So which is my minimum theta and which is my maximum theta? That's the. So and between that, these two thetas, my magnification will be varying. You want to understand this? Okay. So with that, look at this. I got it at some place beyond D. Okay. Suppose I am able to get this at D itself. If I can get it at D, then that's the maximum angle, right? And if the image is formed, before D, I will not be able to see it with my eye. So the maximum I can see is when the image is formed at D. So that is when I have the maximum angle. The theta I will be maximum when the image is formed at D. And when will theta I will be minimum? It will be minimum when the image is formed at infinity. That is, if we keep this object at F, then we keep the object at F. Okay. Now you see, I'll draw another. This is going to go like this, and then that will be like this, see, we go like this. Note that, you see, now you have a smaller theta I. So theta I is here, and then this is my theta minimum. Theta I min is this, when the image is formed at infinity. And when the image is formed at D itself, clearly, you know, from infinity, as you bring it closer and closer and closer, then the theta is increasing, and here you will form the maximum angle, maybe your image something like this, okay, and maybe and that will form an angle like this. So this could be your theta I max. Okay, so there are two cases. Theta minimum will take place, theta I minimum, instrument with the instrument. Theta I minimum will take place when the image is formed at infinity, and theta I max will take place when the image is formed at D. Why? Yeah, I mean, if I bring the image before this, then it will make an even bigger image, but I can't see it. The maximum I can see is when the image is formed at this place, at D. So only this angle is the maximum useful angle for me. Otherwise I can form the image even here also. But then I can't see it. The image has to be at a distance of 25 centimeters for my eye to see. So this is the maximum angle, and when the image is formed at infinity, and that's the minimum. So from there, as I bring it to 25, then this angle is going to shift from theta minimum to to some other value with theta I, and then finally when the image is formed at D, then I have the theta maximum. So those are the boundaries. Let's see the limits of the thetas for me, and theta has to lie between these two values, the minimum and the maximum value. So I need to find what is my theta minimum and theta maximum. And if I do that, then notice magnification will change accordingly. Okay. So the first is this. I'm going to use this expression, right? I'm going to use this lens here. So it's going to be 1 by V. Case 1. Case 1 is when, for this, V is infinity. When V is at infinity, I should say negative infinity, right? Because it is in this direction, so I will say V is at negative infinity, V is infinity. Then what am I going to get? What is going to be the value of U for me? Okay. So that's easy. So I know that 1 by V minus 1 by U is equal to 1 by F. So clearly, so this is a positive number, and this is 1 by minus infinity will be 0 anyway. So I can say that minus 1 by U is equal to 1 by F. So magnitude wise, U is equal to F. I mean, in this case, I am just taking the magnitude, not the sign. Okay, because sign is minus, so I just take magnitude. This U is equal to F. So there, magnification, if we come to that, so in this case, magnification M is going to be equal to D by F. Okay, so that is the magnification I get. Okay. So this is a minimum magnification. Why? Because the image is formed at infinity, theta I is going to be minimum. So that is, so magnification, minimum magnification is this D by F of that. Then what's the maximum magnification? I'm going to say case 2, okay, when V is equal to D. Yeah, so V, image is formed here, exactly at D. So So that's the maximum magnification, right? This is where I get maximum magnification. The theta max will be the greatest. So that would be, how do I find it? Again, I'm going to use the same equation. So 1 by V minus 1 by U equal to 1 by F. Okay. Now I need to find 1 by G. What is V? V is D, so it's going to be 1 by D is there's a positive number 25. So I'll say this is minus D because V is a negative number, right? So V is a negative number. So I'm going to measure it. V is a negative number. So I'll say this is minus D. D is positive, so this is minus D. Then minus 1 by U is equal to 1 by F. So 1 by U is equal to 1 by F minus 1 by minus D, so it will become 1 by, that's what you get. Okay. Anyway, if I take the magnitude alone, then this will be positive, this will be positive. So 1 by U will be like this. 1 by F plus 1 by D. So use it here. So 1 by U, use it here. So that would be, my magnification now is equal to D into 1 by U is 1 by F plus 1 by D. So we take D inside, M is going to be equal to D into D, and we will cancel 1 plus D by F. Okay, so this is the maximum magnification. So this is the minimum magnification, and this is the maximum magnification, and the difference is only 1. So if D by F is say 3.5 or something, then you will get 4.5. If this is 5.5, you will get 6.5. This is 10.3, then you will get 11.3. So that's the magnification range. So from so the magnification value will lie in this range. And suppose this is 3.5 typically, and this is going to be 4.5. Okay. So the magnification can happen between 3.5 and 4.5 range. The image. So this is how you do it. So this is a simple microscope. Okay, I've drawn all these things. I've drawn so many lines in this picture. It's because I want to explain it to you clearly what is happening. But when you draw it for your exam, then you don't need so many lines. Just the one or two lines are enough basically. So the black lines are enough. You can ignore all the other things. Okay? You can ignore the blue lines, red lines, all this can be ignored. Only the black lines will be enough for you. So that would simply be, the picture will be something like this. So this is going to be here, it's going to be C, and I'm going to have something like this. Okay. That's enough. So this is what is required. I've drawn all these lines just to explain the different parts of this derivation. Hope this is clear to you.